Sir, good evening, sir.
Good evening, sir.
Good evening. Can you hear me?
Sir, Rajsekar sir, very good evening, sir. Are you able to hear us, sir?
Yeah, I can hear you, but am I audible?
Yes, sir, you're audible, sir.
All right.
Okay, sir, if you could please check whether you can share your slides, sir.
I guess it is possible. Let me verify.
Okay, sir.
Is it visible?
Yes, sir. Yes, sir, it is visible, sir.
Okay.
Sir, shall I formally have a welcome address and then you may start with the session, sir?
Yeah, please.
Okay, sir. A very warm evening to one and all present here in this virtual gathering. We welcome you all for the AICT ATAL Faculty Development Program. It's a great honor and enthusiasm that I welcome you all to this AICT ATAL Faculty Program. This sharing innovation and skill development in emerging technologies. Today we have the privilege of hosting Dr.N.Rajasekar sir, a distinguished professor of Vellore Institute of Technology, Vellore, and a renowned expert in solar photovoltaics, microgrids, renewable energy, power electronics, and electric drives. With a stellar academic and research background, Dr. Rajasekar has made significant contribution to the field through over 70 journal publications, numerous funded research, patents, and PhD supervision. His leadership in solar energy cells at VAT and his editorial roles in reputed journals further highlighted his expertise and impact. Beyond his research, Dr. Rajasekar has played an instrumental role in advancing education and industry collaboration, evident from his consultancy project with leading organization and his prestigious recognition, including being named among the top 2% scientists of the world by Stanford University. We are truly honored to have him with us today. I am confident that his insights will provide immense value to all the participants. Now, I would like to welcome Dr. Rajasekar sir for the session. Sir, the session is all yours, sir.
Thank you. Thank you for the welcome address. So we will start the session. So I will share it again. I guess my screen is visible, right? Is my screen visible?
Yes, sir, it is visible.
Okay. So I thank Dr. Venkatesh for the opportunity to discuss on the gate drive circuits and production methods for SiC devices. So today we are going to discuss about, first of all, how an SiC gate drive is built and what are all the production methods that are applicable for SiC devices. We will see deliberately. Before to that, let us have an quick understanding. Let us have an understanding of the MOSFETs basically, because whether it is an SiC or it is an SI device or it can be SIJ, the fundamental principle is not going to change. MOSFET is a versatile device that has found various applications, and most probably where we need to have a high switching frequency applications. And it plays a very predominant role until SiC has come in power supplies, because power supply, as we know that switching frequency is mostly made up of switching circuit is mostly made up of MOSFETs, and but has a limitation. When we start with an SI MOSFET, it has a limitation of handling the voltage. So later on, we went with the IGBT. Before we discuss about whether the MOSFET is an SI or is it an SIC, operating principle is not going to change much. It's the same principle that we see with SI. It's extended for SIC as well. Only thing is that SIC can handle a large voltage compared to an SI device. So that is the advantage associated with SIC device. The main reason for MOSFET selection compared to BJT is it is a unipolar device, and it has got a very good switching characteristics in terms of switching speed. MOSFET can be turned on and turned off at a very high rate, so that our passive elements, which we are going to include, if it is any converter, power electronic converter, so naturally the size of the passive devices will come down. So recently, because of the high power density devices, so we are able to accommodate we are able to handle very high wattage within a small square area. And before to this SIC, even SI devices are also able to do that, but with the limitation on voltage. When we look at the device structure, it's vertically oriented, and predominantly we have three terminals: source, gate, and drain. And between the gate and source, we apply the pulses, and the drain and the source, we take the we give the supply. So this device, unlike a BJT, we are going to use only for the application of switching, whereas for an BJT we have two applications. And when I talk about switching, turn on and turn off is primarily done only by a unipolar. That means with a voltage source, with a voltage applied between gate and source, we are able to turn on the device, and it is purely made up of a majority carrier. It's a voltage controlled majority carrier device. There is no point of minority carrier present in its turn on process or during the turn off process. Because of that reason, the device can be turned on and turned off. The switching is so fast that we could be able to achieve a very high switching frequency. But unlike BJT, we cannot see a current path. We are not able to see any current path through the device. If you look at between the source and the drain, it has all been isolated. We cannot see any current flow possible between the drain and source. And this current path naturally happens when your voltage is above the threshold voltage, because of the reason that the voltage is controlling the turn on process. The switching is so fast. Unlike an minority carrier device, we are not injecting anything. We are creating a channel, and that channel helps us to create a link between the drain and the source, whereby a current is established between for the given VDS. It is so important to know that the drain current, the magnitude of the drain current or the flow of drain current is controlled by two factors. One, or it may be established with the help of the gate source voltage. So depending on the magnitude of the gate source voltage, we will be able to say that the current is established between the drain and the source terminal. So the relation between VGS and ID ID with VDS are all very important to understand the characteristics or the operation of this device. So how this happens, how the current flow happens, as I mentioned, we create a channel. So this is the channel that is created beneath the source terminal, the body, the P body, and that creates a flow of current between the drain and the source. The channel is established only when the voltage applied between the VGS is greater than threshold. Below VGS threshold, what happens is there will be, because of the capacitor effect, so the carriers present near the source are actually repelled. Basically, the holes are being repelled. So we try to get free acceptors, and that acceptors are being attracted towards the source terminal, and thereby a channel is actually established. Maybe we'll see that later. Once the channel is established, then there is a current flow possible between drain and source. The creation of this inversion layer or the channel is so fast, so that the turning and turn off, the turn on and turn off is instantaneous in terms of nanoseconds or in microseconds. And most importantly, it doesn't depend on any sort of conductivity modulation, and also it is not it's not going to have any sort of secondary breakdown, because secondary breakdown is one of the important issue that we face with the BJT. And likely, because of there is no secondary breakdown and it is purely a majority carrier device, then we never since we don't have the secondary breakdown and the minority carrier, the on state resistance of the device is quite large. It doesn't have any tail current, and also the on state resistance is comparatively larger between the drain and the source, which actually contribute for the power loss. So one of the major issue with the silicon MOSFET is the value or the presence of this RDS, and this value is contributing to the power loss in the silicon MOSFET, and in a silicon carbide we minimize this RDS on, so that even at a very high temperature we are able to handle a large current. And as I mentioned earlier, there is no secondary breakdown, and there is no negative temperature coefficient. And because of these two effects, especially secondary breakdown happens because of the negative temperature coefficient, the MOSFETs can be easily paralleled. So paralleling of MOSFETs is quite easy because this particular device has a positive temperature coefficient, meaning that whenever your temperature increases, it actually increases the resistance, and thereby you will be allowing a lesser current through that particular device. So that's what we call it as a positive temperature coefficient, and that positive temperature coefficient makes this device most appropriate for paralleling. So when you look at any of the power supply or any UPS, usually switches are connected in parallel. So sometimes we call it as an interleaved architecture, where we parallel. So this paralleling is possible only in MOSFET because it is having a positive temperature coefficient, and this allows to have a current sharing. So these are the advantages associated with MOSFET. But one major reason for as a limitation we can say is its own that means its on state resistance. And most importantly, the on state resistance is going to increase sharply with respect to the breakdown voltage, because breakdown voltage again depends on the dielectric strength of the material. So many factors are involved. So the device structure and to handle the on state resistance, usually the silicon MOSFET is going to have a larger area. to reduce this on-state resistance. Right. Now, it is easy to control. Let us have look at its competitor, or maybe let us have look at its preceder, because MOSFET is usually built after BJT. So BJT is one of the prominent device before MOSFET's invention. And MOSFETs, as we know that it's a majority, it's not a majority carrier device, it's a minority carrier device. It undergoes secondary breakdown. It has a negative temperature coefficient, and most importantly, since it is a minority carrier device, it has the problem of thermal runaway, especially when you try to have paralleling of device because of the negative temperature coefficient. So because of that reason of injection of carriers, BJTs are very much slower than MOSFET, and most importantly, it is a current driven device. So therefore, your drive circuit necessitates for a larger current. So it's actually a current drive circuit. Other than that, we have conductivity modulation, secondary breakdown, and other things. And we can see that. Okay, I think it has by mistake it has come the same thing. So in case of a BJT, there is no channel. We can straight away have a current flow between the collector and emitter, right? So comparing the BJT with MOSFET, BJT is slower, but its on-state resistance is very low because of the conductivity modulation and other effects. So it has a very low on-state resistance. MOSFETs are so fast, its turn on and turn off is very fast, its switching speed is very fast, but it has the problem of high on-state resistances. When you look at the vertical orientation of this MOSFET, we have some few interesting things to look at. One, as I mentioned, it has an any power semiconductor device will have an N minus epitaxial layer, and it has a drift region, and we have a channel on the P body and the source. Here we have a gate source metallization, gate oxide is present, and that is the reason why we are able to create a channel beneath it. When you look at the MOSFET architecture, it has inherent various device combinations. For example, it has an inbuilt BJT possible. You can it has an inbuilt because of the PNP architect NPN architecture. There is a BJT. We can have an intrinsic BJT. We can have a diode. So between your drain and source, we can have the diode, and that PN junction forms the diode. Likewise, we have various parasitic components, especially the capacitance. The capacitance which needs an emphasis here is we have three capacitances which are very, very important for understanding the gate drive circuit. Is the capacitance between the gate and the source, the capacitance between gate and drain, the capacitance between drain and source. So we CGD, CGS, and then CDS. So these are the three capacitances which are very important if we try to understand the MOSFET behavior. Again, based on the charging and discharging of these capacitances, the characteristics of an MOSFET is arrived. So I've shown here the characteristics of an MOSFET as steady state characteristics. And if we look at the steady state characteristics of the MOSFET, the voltage VGS controls the turn on process of the MOSFET. And as we see that there are three states possible: cutoff, active, and then ohmic region. And the travel from cutoff to active to ohmic. So it happens with the application of the VGS, that means the voltage between the gate and the source, and how fast it charges these capacitors. Charging of the capacitors is the most important one with respect to the understanding of the MOSFET. As we know that there are three capacitances, CGD, CGS, and then CDS, out of which CGD is highly nonlinear and it purely depends on the voltage across drain and the source, and it is something very important to know, because this is also something very important to emphasize here. CGS decides your power loss. CGD decides your power loss, and we have other capacitances, CGS and CDS. As we know that the transition from cutoff to active to ohmic, as it is going to happen with the application of the voltage VGS, whenever the voltage is less than VGS threshold, we cannot see any change. Any change in the sense that we are not going to see any change in the current magnitude. If the device is able to conduct current, the device is able to conduct current only when your voltage is above the cutoff. That means above the threshold potential, or the voltage that is necessary to establish the inversion layer. In other words, so below VGS threshold, there is we cannot see any changes. When we see the switching characteristics, we may understand better. So we may not be able to see any change in the current magnitude. You can see change in current magnitude only when VGS is above VGS threshold. When I say that VGS is above VGS threshold, then naturally it enter into the what you call the active and then to ohmic. See here the transition from cutoff through the active to ohmic is very instantaneous, for the reason that if you apply the voltage, when you see that when you apply a voltage, for example, let us take this case, let us take the case of VGS 6, which is having a very high VGS value. So when you apply the VGS value and for a given VDS, the transition to cutoff to ohmic is almost instantaneous, because whenever you have a VDS and if you apply a very large VGS, then naturally the instantaneous change might happen from cutoff to the ohmic value. So therefore, we naturally won't see any effect of this active region, because we try to minimize the turn on process, or we try to minimize the time required to turn on, in the sense that we try to minimize the energy loss during this turn on process. So that is possible only when we give a very high VGS value. When you give a very high VGS value, then naturally the transition from cutoff to ohmic happens without passing through the active region. As I mentioned, there are three important capacitance present in a MOSFET. Drain body depletion layer capacitance, which is nothing but this CGD, and then CGD, and then we have a capacitance between your gate and source metallization, CGS, and then CDS. I think that is nothing but the capacitance between your drain and source. Out of these three capacitances, the largest is the CGS. CGS is the one which is very large compared to the other two, and CGS is almost a constant value. We may not be able to see any change in CGS with respect to VDS value. So your value of CGS is almost same for any VDS. For any VDS, your CGS value is almost the same value. It's not going to change at all. That means the effect of CGS is not going to be that much important. That means it's just charging. So if you have a charge pump, then it is easier. And usually it is a few nanofarads. The capacitance formed between gate and drain, that means drain and body. Drain and body is below the gate source metallization is having a strong influence on the characteristics, especially with respect to the power loss. So whenever your CGD or the region, whenever you are able to charge this CGD at a very fast rate, then naturally you can skip the period called Miller region. So Miller region is actually contributed by this capacitance CGD, and it is a function of the voltage VDS, meaning that whenever you have a very low value of VDS, then you can see two different voltages, two different capacitance value. At a very low VDS, you can have a very large CGD, and whenever your VDS is very large, then naturally your value of CGD will come down. I'll show it in a CGS combination. CGD combination. Now, how we can see these values? How can we see these values, or where we can get these values? Because as I'm talking about capacitance between gate source, gate drain, and then drain source, where these values are given, and how can we know these values? First of all, these values are usually given in a data sheet. If you have a data sheet of a silicon carbide, or if you have a data sheet of silicon MOSFET, any data sheet will have this information in the variable name called CISS, CRSS, and COSS. So these are the three terms they usually mention in the data sheet. Only with that information we will be able to understand what is the value of CGD, CGS, and then CDS. I will show you one picture which will give some information about this capacitance. If you look at, I've given it for two different devices. One on my right, it is actually a silicon. On my left, it is actually a silicon carbide. The silicon carbide device doesn't have any change. So the value of CISS, which is actually a combination of CGD and CGS, is almost the same. That means there is no much effect of drain source voltage on the capacitor value, which is actually good, because whenever your capacitance is keep on varying, then naturally in certain cases we need to go for an variable VGS in order to handle this. But when your VGS, when you try to keep your VGS constant, in a case of where your capacitance is also constant, you can turn on the device at a very fast rate. So therefore, CISS is almost constant. It's such a single or almost the same value, or it is independent of your VDS. Only you can see changes in CRSS. As I mentioned, the change is almost constant for a certain amount of drain voltage, but drain voltage C changes. The capacitance C changes whenever your drain voltage increases, as it is the case of an silicon MOSFET as well. But CISS is almost the same value, and the value of this CISS, COSS is going to change for silicon and then silicon carbide MOSFET. Going back to this, how this will impact. So how the CISS, COSS, CISS will impact on the switching characteristics, and how these switching characteristics, if it is impacted by capacitance, what will be the impact on the gate drive. Those are something very important to understand. As we see that primarily any gate drive circuit, the function of the gate drive circuit is to provide the necessary charge for these capacitance in order to build the voltage. As we see that the charging of this capacitor is basically an RC time constant. How fast you turn on is purely depends on the time constant of this RC component. So by alternatively changing or by adjusting the value of RG, this RC can be varied. That means by changing this in this anyhow this CGS and CDS is a fixed value. Fixed value in the sense it is all defined for a given MOSFET. However, I can still alter its shape or maybe the rise time of this RC component by altering this the gate resistance. So changing the gate resistance, I still have control over how fast I keep the transition from 0 to VGG. So this transition is going to be very important because during this instant between this after this T rise until the end of TF2 is something what you call it as a Miller capacitance, which is purely a function of the given VDS. Since during this Miller capacitance period, you can see changes in your VDS. Before entering into this Miller capacitance, you cannot see any changes in your VDS because the reason is the drain current is able to flow through the device until it reaches this T rise time. Only when we complete this T rise, then only the device will carrying the full current, and at that moment we will be entering into that period called the Miller capacitance period. Why this Miller capacitance is very important? For the simple reason, if you see here at the instant of entering this Miller capacitance, the value is VDS and current is also ID. Both are maximum. But or maybe after if this Miller capacitance is actually 0, let us take it as 0, then in that case it will be very instantaneous. That means from VDS immediately you will come to what do you call the saturated value or maybe VDS on, very small value. This is usually very small. This transition from VDS to VDS on is going to take some time, meaning that I will be carrying full current. At the same time, voltage is also appearing across the device. So the product of these two is going to be the resultant of the energy loss, or what do you call it as an power loss due to switching. This Miller capacitance area or the plateau is very important because if I am able to reduce this plateau, naturally the transition from that means I can completely avoid this fall time. When I completely avoid this fall time, then naturally what will happen is I will be reducing my power loss period. I'll show it in a graph. Maybe later on it will be very clear. So this Miller capacitance plays a huge role. Okay, how can we reduce this Miller capacitance? Again, it again depends on your architecture. So in case of a silicon carbide device, we reduce the value of the on-state resistance and by wafer thickness, and because of that this Miller capacitance area is also getting shortened. But in case of a silicon device, it is actually larger. We'll see that one by one. So what information is sufficient for us to know how much current? Because as we are talking about a capacitor, capacitance is related to charge. So charge is related to the current, right? So purely when you try to design your gate drive circuit, naturally we need to look at how much charge I am supposed to accumulate within the certain time. So that information is usually given in the data sheet. So this is a kind of waveform we can see in any of the MOSFET data sheet, where you can see that this QGD is usually mentioned in the data sheet value as QG, and this will tell us how much is the amount of charge required to turn on. And if you try to if you want to turn on the device within a specified time period, so as we know that I is equal to dq by dt, once you know the time and the charge required, then you can easily decide how much current the gate drive should supply. So your gate drive current is very important in order to drive, because that decides your power consumption of the drive circuit. So this information of QG is available only in datasheet. Only after getting this information, we'll be able to start designing, or maybe as a preamble, we are able to get this information from the datasheet, and then we can start designing the gate drive circuit. All right. When we look at the switching performance of the device, before to that we should understand understand one factor, that silicon device and silicon carbide are quite different, in the sense that parameters vary. That means its on-state resistance is different, its CGS, CGD, all the values are different. Its structure itself is in the sense that the area occupied is also very limited. So first, if we try to understand the performance, we should know what are the existing differences between the silicon and the silicon carbide device. Let us try to understand by looking at every single parameter, starting from on-state resistance. So when you look at the on-state resistance of this silicon and silicon carbide device, the silicon carbide device on-state resistance is way down than the on-state resistance of an silicon MOSFET. So it's basically the chip, the size. So how much area or how much breakdown voltage we can, that is with respect to the VDS. So you can see that the dielectric breakdown field strength of silicon carbide, because again it depends on the drift region, right? So this SiC MOSFET is approximately 10 times higher than that of a silicon. And as we know that this breakdown voltage or dielectric strength is related directly with the resistance of the device. So in order to have a compromise, you try to reduce the, if we go for a large breakdown voltage, then we have to make a compromise on our on-state resistance. Compared to silicon, it is far below than the silicon MOSFET, but still comparatively some amount of resistance is present in a silicon carbide device, but comparatively lower than IGBT. If you look at the drift layer resistance of the silicon carbide is lower than the silicon MOSFET, for the reason that the breakdown voltage. So more the breakdown voltage, so naturally it has an impact on the drift region or the drift layer. Right. When you look at the conduction loss of an of three different MOSFET, silicon, silicon junction, and then silicon carbide and GaN. The very low value of conduction loss occurs only with silicon carbide, and that too happens even at very high temperature. You can see that there are actually two temperatures present. One is for 125 degree, the other one is for 25 degree. So both the values are very large for the current RMS. So if I'm trying to handle a large amount of current at a very high temperature, naturally the conduction loss is very high. That means leading to the breakdown of the device. Whereas the silicon carbide device, SiC, can still handle a large current even at a very high temperature. So the temperature, whether it is at 25 degrees centigrade or it is at 125 degrees centigrade, we are able to handle a large amount of current with a very low temperature rise. Then, how is it possible? This characteristics of handling a large current with a very low resistance is possible or happens to happening only because of its low on-state resistance. The on-state resistance of the device is usually very less. compared to for any temperature. It's actually very, very less compared to the other competitors, maybe SI or it can be GAN. And the on-state resistance ratio with respect to on-state resistance at different temperature ratio, if you look at with respect to VGS, if you keep a higher value of VGS, then naturally the on-state resistance is very, very small. This is also one of the reason why we try to keep a voltage of somewhere around 18 volt in case of an silicon carbide device, though in case of a silicon MOSFET, we try to keep somewhere less than 15 or up to 15 volt. But for a silicon carbide, we try to keep a very large VGS for the reason that we try to have an very low on-state resistance. As we know that on-state resistance contribute for the conduction loss. Then one of the important point that we that is something to be discussed here is the change, the change in the drain current with respect to that VDS. For a given VDS, you can handle a very large amount of current with a VGS value of greater than 18 volt or maybe 18 volt. If you apply, then naturally the current that is being carried by the device is able to handle the current with a very low VDS. So that means its on-state voltage drop. Its on-state voltage drop is actually very small. VDS on is very small. As we were discussing this point earlier, the effect of capacitance is predominant in the switching characteristics, and that is nothing but the charging of these capacitances, these three capacitances, and how fast we charge this capacitor decides your losses. And one more factor which is something noteworthy to mention here is the charging. If you try to do it with a with the help of an RC, and if you try to do it at a very fast rate, that might also trigger some losses as well. So we have to be very cautious in choosing the value of RG. We'll see that because it might lead to ringing, because silicon carbide devices are subject to ringing effect compared to any other device, whether it may be a silicon MOSFET or it can be an your IGBT. So this ringing is something existing in case of an SiC device because of the resistance that is present on the device. All right. So if we look at the value or how we are going to handle the current for a given VGS, even for any temperature, whether it is 25 degree or up to 150 degree, for a given VGS, the change from 0 to the higher value, the change from zero current to the full potential or the full rated value, it requires a small change in VGS. The change in VGS, I am talking about change in VGS, though VGS is 18 volt. So you can see changes from 4 volt onwards when you have a temperature of 25 degree, and the change is clearly visible from 3 volt onwards when it is at 150 degree centigrade Celsius. And this change in VGS, which is contributing for the current that is able to carry that is to be carried by the device, is so fast. That means the change, I am talking about this point. I'll show you this one. So this change that is actually contributing for the drain current is so fast that it is able to turn on faster. All right. Now, as I mentioned, in case of a silicon and silicon carbide device, whether it is any of this device, we need to develop a gate drive circuit, and that gate drive circuit has to turn on the device at a very fast rate. when we try to turn on the device, naturally we need to add an element at the gate terminal of the MOSFET. So we call it as an external gate resistor. In addition, for a silicon carbide, we have an internal gate resistance as well. But in a silicon device, we talk about only this RG external. And this RG external has multiple roles to play, because this decides your ringing. This decides your what you call malfunction, or what there is one point I have mentioned it. I'll show you in that point. When the point comes, I'll tell you what it is. Forgot. Where is that point? 1 minute. It was there earlier. Yeah, self turn on. So this self turn on as well as ringing is decided by the value of RG that we choose. And how can we arrive at this RG? RG is to be defined based on the amount of current that you want to handle. How can we arrive at the current? The current is again depends on how much amount of charge you want to store inside the capacitor within the stipulated time. So eventually, when you want to reduce your rise time, when you want to reduce your overall time delay during turn on and turn off, naturally the only controlling factor, the only factor that you can control is the rate of change in gate voltage, gate source voltage, and then the RG. That means the gate resistance that is connected externally. Only by changing these two values, we are able to handle. We are able to determine only we decide these two values. Then these two values will decide how much is your gate drive power requirement. So therefore, QG, as I mentioned, available in the data sheet, gives us an information about how much will be the change in voltage. The change in voltage along with the decided value of RG we will come to know how much is the peak current that can be supplied. As we know that these devices, whether it is a MOSFET made up of silicon or silicon carbide, is going to form a power converter circuit. And these devices which are going to behave as a switch is to be turned on and turned off by means of a control pulses. These control pulses are naturally, or maybe these pulses are actually generated using a microcontroller. Microcontroller, a maximum of 5 volt you can expect, with a current driven capability of somewhere in milliampere. But when I want to turn on the device faster to minimize the switching loss, then naturally we need a circuit between the pulse generation unit and then the MOSFET which we are going to use. So that is what you call it as a gate drive circuit. A gate drive circuit, its primary role is to have the current amplification, the most important one, and also the voltage amplification. We need to have the sufficient voltage between your gate and the source, and the sufficient amount of current that is required to charge these capacitors. Most importantly, the circuit must provide path. The circuit must provide path for the current flow, especially for charging and also for discharging of the capacitances. So a charge circuit or a gate drive circuit is going to serve the purpose of transferring the charge from the gate drive circuit, transfer the charge through the gate drive circuit to the MOSFET, and take out the necessary charge which has been already stored during turn on process. So it should serve both the purpose. That means it should also provide source and it is also a sink. So we need to have a basic understanding of that. Now the question is, how much will be the size of the gate drive? As the picture clearly indicates, how much power you are going to handle and how much charge you are going to pump inside your MOSFET, right? That decides naturally your gate drive circuit capacity. So the job or the primary role of a gate drive circuit is always one, whether it is a MOSFET of a lower rating or it is a MOSFET of a very high rating. The role is same. That means it has to provide the necessary charge that need to be stored inside the capacitor for turn on of the device and also provide the path for the discharge of the stored charges. So with respect to that, the drive circuit will vary. For instance, I cannot use a drive circuit which can able to provide a charge of only 0.16 microcoulomb for the circuit which actually requires 12.6 microcoulomb. So it cannot be. It is not possible because the input capacitance is completely different. Therefore, the drive capacity of your MOSFET is purely decided by the power rating of your MOSFET. How much is you are going to handle, and any of the gate drive circuit is going to do only one job. It is going to charge and discharge, and how fast you charge and discharge these capacitances is going to decide how much you can minimize this area. How much you can minimize this area, because as I said earlier, the current once it reaches, for example, I think here the current is not given, but still I can say with respect to this, until it reaches the threshold, there is no current. But once it reaches threshold, the current starts increasing, and when it reaches this T1 and T2, the current will be reaching the peak and then it will settle down. So this area we try to minimize. So how can we minimize that? So by reducing this Miller capacitance area and also by choosing an appropriate RC time constant or by choosing an R value. As I mentioned earlier, any microcontroller can provide only milliampere of current. Naturally, we need a circuit in between your microcontroller and then your MOSFET, right? How much impact will this CGD will create? You see here, this area is going to decide how much is going to be the loss. So maybe in one or two slides later on, I will show you how much is the exact energy loss that happens in case of an silicon carbide, IGBT, and then a MOSFET. So these three devices we will see. We'll try to see. And if we try to minimize this Miller capacitance, then naturally we will be able to reduce your switching time. Whenever you reduce your switching time, efficiency of the device will be very fast. And one issue that might get introduced because of this effect, or maybe reducing this Miller capacitance, is the EMI, because it is going to create ringing. As this ringing is purely decided by your resistor value, that is also important to note down. And if the ringing is when the ringing happens, then naturally it leads to an EMI issue. Okay, so what are the basic requirements of my gate drive? My gate drive requirement, the first and the foremost is it must provide sufficient voltage for the device to turn on. For instance, I may require a voltage of maybe 18 volt, 15 volt, or maybe 12 volt, depending on my device selection. Whatever the voltage I require, that the device must be able to, that drive circuit must be capable of providing it. Then the drive must be in a position to adjust. The drive must be designed in such a way that it must charge the capacitances at a very fast rate so that your turn on is faster. So if you want to achieve a faster switching speed, naturally you need to have a adjustment in your gate drive or what you call it as an resistance value RG. As I mentioned, there are two RG present in case of an SIC, but for an SI, it is going to be only one resistance as it is shown here. And as we know that the capacitance of CGD or maybe the stored charges in the capacitance need to be discharged. So we need to provide a path for it. So we are trying to add a resistor here. In general, this is the only this is the only resistor we try to add. We try to add here. 1 minute. Okay, we try to add here when we try to design the gate drive circuit. Okay, what will be the effect of this RG? Because I was keep on saying RG has an effect on the switching characteristics. It is clearly visible. Depending on the value of your RG, your current VDS, your ID, current ID, and also the VDS, the instant at which it reaches the full voltage or at which the voltage comes to the what do you call the on state voltage drop is decided. So higher the gate drive resistance or what you call the external gate drive gate resistance, naturally it will take a longer time to settle down. So when it is a longer time to settle down or maybe the fall time when it is more, then the area to be covered for the power loss is also quite large. I think this will make sense. This picture will make sense as I was mentioning about the SIC MOSFET and the IGBT. As we see that the area, the amount of power loss, the switching loss in case of an IGBT is quite larger because the area covered is quite large, whereas the area which is occupied by the silicon carbide MOSFET is actually 9 times smaller because it's very small. It is clearly visible. It is somewhere around 900 microjoule and here it is somewhere around 100 microjoule. So the area covered or the loss that happens because of the switching is going to be very small for a SIC device compared to an SI device, which can be an IGBT or it can be a MOSFET. And also one point I'd like to share here is whenever we go with an SI IGBT, its switching loss is very less compared to the MOSFET. So therefore, we can straight away have a comparison between SIC MOSFET and then IGBT. And the switching losses due to the SIC MOSFET is actually very small. But one problem is introduced. That is nothing but though the area of your power loss is very small, but it has ringing. So ringing leads to EMI problem. So this ringing has to be minimized. So ringing is primarily because of two things. One, because of your selection of R. So as I mentioned that external gate resistance RG external and also the lead inductances. So if you have lead inductances because of your PCB layout or because of your wire cable length, then naturally this ringing effect will be larger. So whenever you have a whenever you keep your drive circuit far away from your MOSFET, then naturally it needs a lot of wire or maybe the routing. So in that sense, we are supposed to handle it. We are supposed to give up in the form of an ringing. So when you want to minimize that ringing, then naturally you need to keep your drive circuit very close to your switch. So in certain cases, we can see that the driving circuit is directly integrated on the body of the MOSFET. So that's how it is. All right. What are the other forms of gate drive circuit? As I mentioned, any gate drive need to provide the necessary voltage. So generally, a voltage shift is one of the major requirement for the gate drive circuit. So it can be from a push pull configuration, or it can be from an digital logic, whatever the controller, and then using a MOSFET switch, we can have a voltage drive voltage conversion. So in any of the case, in both of the cases, the voltage is actually amplified, and drive voltage conversion has the limitation of the resistance added to the circuit, so that the gate drive is actually it will have a large power rating, whereas in case of a push pull configuration it can be avoided. At the same time, push pull configuration can provide sufficient amount of charge to drive the MOSFET. Alternatively, for a high side driver, we can add a bootstrap capacitor or maybe a high side driver, where we have a additional capacitance which will support the sudden requirement of the charge while we try to turn on, and also it provides the path for absorbing the or discharge of the capacitance from the or discharge of the charges from the MOSFET to the drive circuit. All right. Generally we try to use these gate drive circuits with an optocoupler, so which is very familiar. We try to use an optocoupler or a photocoupler, where we have an light emitting diode and it is optically isolated, and most of the IR2 all these are basically have an opto isolation and try to provide pulses. Um, some of the popular optocoupler are TLP series, starting from 250, it can go up to 650. So that is the number, TLP number you can use. So different optocouplers are available for isolation purpose. Okay, let us see how generally the gate drive circuit will look at. So it will have a 3.3 volt. We generally have a 3.3 volt, maybe up to 5 volt or 6 volt from a microcontroller, and that voltage is actually amplified to the level of somewhere around 18 volt to 12 to 18 volt with the help of this intermediate circuit. The power required, the energy required to turn on is actually supplied with the help of this additional arrangement. So push pull configuration. So the gate charge speed is going to decide your switching speed of your MOSFET. We can also use a gate drive circuit similar to an single channel 4 ampere gate drive. But as we know that the primary role of an gate drive circuit is to provide the necessary charges, but there are some additional features required for a gate drive. One is to have shutdown. So you may need to have an option to shut down the device whenever it is faulty, and also we need to have production of negative voltage as well. So those things are not possible in this configuration, whereas we can go for a circuit with a TLP series where it provides the necessary voltage. Right. As I was talking about the influence of the cable length, as we know that cable length plays a major role. So whenever you keep your gear drive far from your device, then naturally this cable length introduce inductance. So this parasitic inductance in combination with the capacitance, they form the resist ringing, that is LC. So we need to have an RCD snubber to reduce this ringing. This is one of the option. Or in certain cases, I think that slide I have not added, but I'll show you. We can, in certain cases, to a certain extent, first of all, to a certain extent, we can avoid this ringing by changing the RG value. We'll see it in the next slide. So by changing the RG value, we are able to handle this ringing. The second way, by adding an snubber, we can handle this. Or we try to keep the gate drive very close to your MOSFET so that the ringing effect can be minimized. So either of this way, we try to minimize the the ringing effect that is happening or occurring in the MOSFET switches. Okay, we are talking something called self turn on. What is self turn on? As I was talking, something related to how fast you charge the device. How fast you charge the device. That decides your turn on process. So whenever you try to charge the device, one more case also we should consider. One of the capacitors is going to discharge. One of the capacitors is going to discharge. One side you are charging, the other side we should provide the path for the discharge. Especially this happens in case of a MOSFET, especially in the case of an inverter where we keep two high side and low side device. So what will happen is when I try to turn on the lower MOSFET, though my device is trying to turn on the lower MOSFET Q2, I am trying to turn on, the current that is carried through the device creates a high dV by dt. One thing that I have not mentioned in the beginning, you have to be little careful about your RC time constant, in the reason that it should not have an false trigger. That means the peak overshoot. That means the overshoot created by rate of change of voltage. Whenever you are high, whenever the device encounter a high dV by dt, then naturally the chance of self turn on is very high. To avoid that self turn on, we try to go for some protection. So general protection circuit against self turn on, against this large dV by dt, is by using a simple capacitor, or it can be called as an Miller clamp capacitance or Miller clamp circuit. We will see that next. What will happen if there is no clamp capacitance, or if there is no Miller clamp circuit? What happens is Q1 also get turned on. You can see here, whenever you keep your RG very large, that is also important. Your value of RG is also equivalently important. So whenever your RG is very large, sufficient enough, naturally the rate of change in the value, that means dV by dt, induce, or that across this gate and the source of the other switch will try to turn on the switch that is actually off. So this self turn on can be avoided by connecting a capacitor between gate source, so that this provides the necessary current path. This provides the necessary current path. Now, this can be also done with the help of the gate source capacitance, or also by means of adding an active Miller clamp circuit. Right. Now, we talk about a negative surge. So as you know that the rate of change, so one is rate of change in current and also rate of change in voltage. So this both the rate of change contributes to spurious turn on. That means without the actual gate pulses, the rate of change in voltage is trying to turn on the device. So this can be avoided by connecting a diode between the gate and the source. So generally, we try to have, we try to keep some protective measures so that the gate drive circuit is capable of providing the necessary voltage and the necessary charge. All right. So this is one of the commercially available SIC driver specifications. And let me share some. 1 minute. I'll just share you one of the. Okay. Now I have taken the data sheet. So this is the data sheet of an MOSFET data sheet, and this MOSFET data sheet has. So I have taken the data sheet for. Let me share it one after the other. 1 minute. So this is one data sheet, and another data sheet. So this is another data sheet. So I have kept two devices side by side. One is a normal silicon MOSFET. The other one is a silicon carbide MOSFET. You can see here. Let us go one by one. First and the foremost is when I try to use a silicon MOSFET. Yes, it can have an high dV by dt. It can handle fast switching, easy parallel. It's quite general, common for any MOSFET. But something that is which needs our attention is this RDS on. You see, an RDS on of 0.85 is happening in case of a silicon MOSFET, whereas an RDS on of only 14 milliohm, which is almost 10 times lesser than the value what we are talking about. So it is very, very small. RDS on is very small, and because of that, the switching loss is also very small. Then, if you look at the charge, let us see it from here. Okay. If we look at the charge, I think it might be available. Yeah, QG. Let me minimize it. Okay, fine. If you look at the charge, here it requires 63 nanocoulomb, whereas the amount of QG required for my silicon carbide is somewhere around 145. So when I see the both the devices, the silicon device is going to consume only a very small amount of charge to turn on, whereas the amount of charge required to turn on my silicon carbide is very large, or at least 2 times, right? So therefore, when I go with this QG, then naturally within a shorter time, if I try to do that, then the amount of current that need to be given or to drive in is also going to be very large. Then what this QG will be, or where can it affect? QG effect you can see in case of this rise time. Generally, there are formulas to find the values for TD on, delay time, rise time, and then fall time. All those values you can find out. Let me show you where you can find out or how it can be determined. Yes, it is somewhere here. Yeah, Toshiba. You can find out the values of how much is your rise time, fall time, and then the Miller plateau, the whatever the time period, you can find out with the help of the values given in your data sheet. But these values, even if you compute, theoretically it won't usually match, because QG decides your amount of current and not purely on the value of CGS alone. Or maybe we can say that it also depends on what voltage of VGS you apply. So there are so many factors involved, but still theoretically if you want to compute this rise time, fall time, it can still be computed with the help of these equations. All right. So comparing again back to back your silicon with the silicon carbide. So it takes here we are talking about TR, right? Yeah, TR. Yeah. So here it takes rise time of 29 nanoseconds, and here it takes 23 nanoseconds. Though it seems to be very less for a silicon, but you see the amount of current that is been handled. The current that is handled is somewhere around 53 ampere, 54 ampere compared to 8 ampere. And also the amount of voltage we are going to handle is somewhere around 800 volt compared to a 250 volt. And the gate resistance is usually very small. You see that RG on, it is usually very small in order to have a faster turn on. And this turn on energy required for for the case of an silicon carbide device is usually very high compared to an silicon MOSFET. So other things we can look at it. Maybe one important thing alone we will see. One important thing we will see, that is nothing but the comparison between this Miller. You see here the Miller plateau. That means it is not actually flat. Whenever you provide the rate of change in VGS, very large, and if that rate of change happens at a very small period, then naturally even you can quickly skip this VG period. That means this Miller effect. When the Miller effect is minimized, then naturally the on-state resistance is also going to be on-state resistance, as well as the on-state switching loss is also going to be very, very small. So that is something that we need to understand. Okay. Okay. One last point which I have not discussed. I'll just add one last point. Last point, 1 minute. I'll just take that particular slide. Yeah. I'll share this particular slide. So when you want to minimize, this ringing, you can have one more terminal called Kelvin connection, which has a built-in surge protection. So we have been talking about something called an diode connected between the gate and the source. So they have an option. They have an additional terminal here. With the addition of this Kelvin, so we are able to handle the switching loss. So switching loss in a silicon carbide device can be handled with this Kelvin pin. So that one information I want to share. I think with that I will stop my presentation. If you have any questions, I'll be happy to answer.
Sir, it was a nice presentation, first of all.
Yeah.
Sir, there are a few questions in the chat box. First one is, how do conduction losses vary with temperature in semiconductor devices like MOSFET and IGBTs?
Actually, I'll show you one slide. So if you see here, I've added. So this is how the conduction loss happens. So the amount of current that is being carried and the on-state voltage drop across the device is going to decide how much will be your conduction loss, conduction energy loss. and this loss is purely depends on your RDS on. So RDS on is actually very small in case of your SiC device, and because of that reason, the loss that is happening due to this MOSFET, silicon carbide MOSFET, is also very small. And for the case of an IGBT, I think it is going to be very large, both the switching and also compared to silicon carbide device. Compared to silicon, IGBT has a lower value, but compared to silicon carbide, IGBT has a higher value, at least 9 times higher. Is that okay?
Yes, sir. Yes, sir. One more
Okay.
question, sir. What techniques or materials can be used to reduce conduction losses in high power applications?
Materials in the sense I couldn't understand exactly what question, what they want to ask. You can reduce the switching loss because you can avoid the ringing by adding a resistor or by changing the RG value. You can avoid the ringing. That is possible because ringing is a predominant effect of a silicon carbide device. But other than that, conduction loss with respect to the material in the sense, okay, we can say it in this way. For example, if you consider the PCB track, if you are able to increase the width of the PCB that to carry the same current, then naturally you will be able to reduce the stray inductance, the parasitic inductance, and that might reduce further losses. That way only we can handle. Otherwise, in terms of material, I couldn't understand exact question what they want to ask.
So I hope it is a device. It is not materials. I hope the device which has been used.
Device in
What
the sense,
techniques? Uh, Let it be a MOSFET or IGBT.
no,
Techniques
you
are
say techniques in the sense, you are you are you do you want to know about what are the different gate drive circuits you are asking, or
they have asked something like that, sir.
I think the question itself is not clear. But
Clear,
anyhow,
yes, sir.
there are various gate drive circuits possible, and the simplest one is using an optocoupler. You can generate the pulse using a microcontroller, use an optocoupler, drive your switch. That's the easiest. But you need to have
Tha-
an auxiliary power supply
yes, sir. Yes, sir.
floating.
Thank you, sir. Thank you, sir. I hope
Okay,
the question is clear. The answer is clear for the audience.
all right.
Thank you very much, sir.
Yeah.
It was really a nice presentation, sir. We had a very good opportunity to note the values. You have really demonstrated how to note the values from the data sheet and what are all the factors which will be affecting. It was a clear presentation about the gate drivers, sir. Thank you very much, sir. Thank you for
Okay.
accepting our invitation and
Thank you.
presenting this uh, nice lecture, sir.
Thank you so much. Thanks for the
Thank you.
opportunity.
Thank you, sir. Thank you, sir.
Thank you. Thank you.
Participants, the feedback link is here. You can just complete the feedback link. The session is formally closed.
Okay. Thank you.
Thank you, sir.